Hey everybody, welcome back to trigonometry. Today we're in section 5.4 looking at the sum and difference identities for sine and tangent. So in this section we'll learn the sum and difference identities for sine, the sum and difference identities for tangent, that's 4 separate identities, and then we'll do a few application problems with those where we'll calculate a few exact values, and we will also do some proofs involving these identities. So let's get started. So the first thing we're going to do is write down all 4 of our new identities. For the sine function, we have the sine of a plus b equals the sine of a times the cosine of b plus the cosine of a times the sine of b. And then the other one says the sine of a minus b is equal to the sine of a times the cosine of b minus the cosine of a times the sine of b. Now just for comparison, let's look again at the identity for cosine of a plus b and cosine of a minus b from section 5.3. You'll remember that the cosine of a plus b has a minus sign in the formula, and the cosine of a minus b has a plus sign in the formula. But that's not the case for the sine of a plus b and the sine of a minus b. For the sine identities, if the argument contains a plus, then the formula contains a plus. And if the argument contains a minus, then the formula contains a minus. It's easy to get those mixed up, so I wanted you to have a chance to look at them all together. When you're dealing with cosine of a plus b and cosine of a minus b, the signs in the formula are opposite from the signs in the argument. But when you're dealing with sine of a plus b and sine of a minus b, the signs in the formula are the same as the signs in the argument. Let's go ahead and also write down the identity for the tangent of a plus b. That's equal to tangent of a plus tangent of b all over 1 minus tangent of a times tangent of b. And then the identity for the tangent of a minus b is very similar. You can see that it's built exactly the same way, but the signs are different. So the tangent of a minus b is equal to the tangent of a minus the tangent of b all over 1 plus the tangent of a times the tangent of b. So note the 2 sign changes that we see here. So we want to get some practice using these new identities to calculate some exact values. So let's look at example 1. Here in part A, it says find the exact value of the sine of 75. Now we do this exactly the same way that we did for the cosine values in section 5.3. We want to think of 75 as a sum or difference of 2 angles whose exact function values we already know. So we're going to have to find a way to write 75 degrees as a sum or difference of either 30, 45, 60, or any angle that has one of those as its reference angle. Now this one's easy because it's pretty clear that 75 degrees can break down into 30 degrees plus 45 degrees. And because of this plus sign here, we know that we're going to want to use our sine of a plus b identity. So I'm going to copy that here so we can look at it while we use it. So now let's write the sine of 75 degrees is equal to the sine of 30 plus 45 degrees. So when we plug into our identity here, 30 degrees will take the place of A, and 45 degrees will take the place of B. So here we go. The sine of A times the cosine of B is going to be written as the sine of 30 times the cosine of 45. Then we have a plus, and then the cosine of A times the sine of B is going to be cosine of 30 degrees times sine of 45 degrees. Now we plug in our known values. So the sine of 30 degrees we know is 1/2. Cosine of 45 degrees is square root of 2 over 2, plus the cosine of 30 degrees, which is square root of 3 over 2, times the sine of 45 degrees, which is square root of 2 over 2. Of course, now we multiply our fractions together. So 1/2 times square root of 2 over 2 will give us square root of 2 over 4. And then square root of 3 over 2 times square root of 2 over 2 will give us square root of 6 over 4. And just like we saw in section 5.3, it's fine to leave your answer in this form, or you can combine these 2 terms into a single fraction with one denominator. Okay, now let's see what we can do with part B. Find the exact value of the sine of 17 pi over 12. Of course, we know that in order to get the exact value, we need to write this as the sum or difference of two angles whose function values we know. But it's hard to see how to break this down when it's written in radians. So let's convert 17 pi over 12 radians into degrees. We know all we have to do is replace pi radians with 180 degrees. So now we have 17 times 180 degrees divided by 12, and that works out to 255 degrees. Now there are lots of ways we can break this down, but the first thing I notice is that the last digit here is a 5. That tells me that one of the angles I use needs to either be 45 or something that has a reference angle of 45, because all of those numbers end in 5. So if you think to yourself 255 degrees equals 45 plus something, then you subtract and you find out that the something has to be 210 degrees. So we'll write 255 degrees equals 45 degrees plus 210 degrees. Now, because this is a sum, we know that we need the identity for the sine of a plus b, so here it is. So now the sine of 17 pi over 12 is equal to the sine of 45 degrees plus 210 degrees. And so we are going to plug into our identity using 45 degrees in place of the a and using 210 degrees in place of the b. So here we go. Sine of a would be sine of 45 degrees. Cosine of b would be cosine of 210 degrees. Then we have our plus. Then cosine of a would be cosine of 45 degrees. Sine of b would be sine of 210 degrees. And now we're going to substitute our known values in here. Now we know the sine and cosine of 45 degrees by heart, but what about the sine and cosine of 210 degrees? Let's come over here and jot down a diagram to help us figure that out. So we know 210 degrees would be in the third quadrant, and it would have a 30-degree reference angle. So the sine of 210 degrees is going to be negative sine of 30 degrees, so negative 1/2. And the cosine of 210 degrees is going to be the negative cosine of 30 degrees, so negative square root of 3 over 2. Now that we have that, we can go ahead with our substitution. So the sine of 45 degrees is equal to square root of 2 over 2. Cosine of 210 degrees, we know, is negative square root of 3 over 2. Then we have our plus. Cosine of 45 degrees is going to be, again, square root of 2 over 2. Sine of 210 degrees is going to be negative 1/2. As usual, now we will multiply our fractions together. So square root of 2 over 2 times negative square root of 3 over 2 will give us negative square root of 6 over 4. And then when we multiply the fractions in the second term, that would give us negative square root of 2 over 4. But we've got a plus sign here. So instead of writing plus negative, we're just going to write minus square root of 2 over 4. So this is our final answer for the sine of 17 pi over 12. And you can leave it in this form, or you can write it as a single fraction. But if you do write it as a single fraction over one denominator, make sure that the negative on this first term goes in front of the first term in your fraction and not in front of the whole fraction. Now here in part C, we're going to get to practice with the tangent identities just a little bit. So it says find the exact value of the tangent of 165 degrees. Now, just like before, we know that the way to approach this is to break 165 degrees into two angles whose function values we know. And again, I see that this angle ends in a 5. So I probably want to try to break this down into 45 plus something. So we know that 165 degrees can be thought of as 45 degrees plus 120 degrees. And because we have written this as a sum of two angles, let's take a look at the identity for the tangent of A plus B. So we have the tangent of 165 degrees is equal to the tangent of 45 degrees plus 120 degrees. So when we plug into this identity, 45 degrees will take the place of A, and 120 degrees will take the place of B. So here we go. The tangent of A plus the tangent of B will be tangent of 45 degrees plus tangent of 120 degrees, and that's all over 1 minus the tangent of 45 degrees times the tangent of 120 degrees. And now we're ready to substitute our known values in here. So we know the tangent of 45, but we might not have the tangent of 120 just off the top of our head. Let's start by looking at a diagram of 120 degrees. You can see that's going to have a reference angle of 60 degrees, and we know tangent values are negative in quadrant 2. So the tangent of 120 degrees is going to be negative tangent of 60 degrees, so that's negative square root of 3. All right, so now substituting our known values in here. The tangent of 45 degrees is 1. Then we have plus. The tangent of 120 degrees is negative square root of 3. That's all over 1 minus the tangent of 45 degrees, which is 1, times the tangent of 120 degrees, which is negative square root of 3. Okay, now let's clean this up a little bit. We have 1 plus negative square root of 3 in the top here. We know we can write that as 1 minus square root of 3. In the bottom, we have 1 minus 1 times negative square root of 3. So minus times negative is going to give us plus. So we'll have 1 plus 1 times the square root of 3, which is square root of 3. Okay, now we can't leave our answer in this form because there is a radical in the denominator, so we know that we have to rationalize this denominator. And because we have 2 terms in the denominator, in order to rationalize, we have to multiply by the conjugate of this denominator. So that means multiplying by 1 minus the square root of 3, and because we're doing it to the bottom, we also have to do it to the top. So as you know, in order to do this multiplication in the top and in the bottom, we will use the FOIL method. So I'm going to go ahead and draw us a big fraction bar here, and now here we go, FOIL method in the top. First times first is going to be 1. Outer times outer is going to give us minus square root of 3. Inner times inner also gives us minus square root of 3. And then last times last is going to give us plus 3. In the denominator, first times first gives us 1. The outer and the inner will add up to 0 because these are conjugates. And then last times last, this time is minus 3. So now we want to combine like terms in both the top and the bottom. So in the top, 1 plus 3 is 4. And then for our radicals, we have minus 1 square root of 3 minus 1 square root of 3. That's going to give us minus 2 square root of 3. In the denominator, we have 1 minus 3, so that's negative 2. Now we know that this can be reduced because all 3 of these numbers can be divided by 2. So what we'll do is split this into 2 fractions. We'll have 4 over negative 2 minus 2 square root of 3 over negative 2. The first term where we have 4 over negative 2 will reduce to negative 2. And the second term, where we have minus 2 square root of 3 over negative 2, we know minus negative is going to give us plus, and then our 2's divide out, so we just are left with square root of 3. So our final answer for the tangent of 165 degrees is negative 2 plus square root of 3, or you could reverse these terms so that the positive one comes first, and you could write it as square root of 3 minus 2. Either one is perfectly acceptable. And here in Part D, we're asked to find the exact value of the tangent of 13 pi over 12. Now, just like before, it's hard to see how to break this down when the angle is written in radians. So the first thing we want to do is convert this to degrees. And we know that all we have to do is replace the pi with 180 degrees. So 13 pi over 12 becomes 13 times 180 degrees over 12. And that works out to 195 degrees. Now your first thought is probably to do this like we did in Part C. So you see the 5 here, and that makes you start thinking about 45 plus something else. So 195 is 45 plus 150. Let's go with that. Because we see the plus sign here, we know that we'll want to use the tangent of A plus B formula. And we know that 45 degrees is going to take the place of angle A, and 150 degrees is going to take the place of angle B. So we're going to need to know the tangent of 150 degrees. Let's go ahead and figure that out. Of course, 150 degrees has a 30-degree reference angle, and tangent values are negative in quadrant 2. So the tangent of 150 degrees is going to be negative tangent of 30, so that's negative square root of 3 over 3. Now to plug into our formula, we know that we've broken down 13 pi over 12 into 45 degrees plus 150 degrees. So in our formula, that's going to be tangent of 45 degrees plus tangent of 150 degrees all over 1 minus tangent of 45 degrees times tangent of 150 degrees. And now let's plug in our known values. The tangent of 45 degrees is 1. And then we have our plus sign. And the tangent of 150 degrees is negative square root of 3 over 3. Then we have our fraction bar. And in the denominator we have 1 minus tangent of 45 degrees, which is 1, times the tangent of 150 degrees, which is negative square root of 3 over 3. Now this does look a little messy at this point because we have a fraction made out of fractions, so we know we're going to have to simplify this. Let's start by working on the signs here. In the top we have 1 plus a negative value. So plus negative is actually minus. Let's rewrite the top as 1 minus square root of 3 over 3. Then in the denominator we have 1 minus 1 times negative square root of 3 over 3. Minus negative is going to make plus. So then we'll have 1 plus 1 times square root of 3 over 3, which is just square root of 3 over 3. Now the next thing to do is to eliminate the little denominators. And we know that in order to do that, we multiply top and bottom by whatever denominator we're trying to cancel out. Here it's a 3, so I've multiplied the top by 3 and the bottom by 3. So now distributing these 3's, in the top, 3 times 1 is 3, and then we have minus 3 times square root of 3 over 3. Now for the denominator, distributing this 3, we have 3 times 1 is 3, and then plus 3 times this fraction, which is 3 square root of 3 over 3. In both top and bottom, these 3's will divide out, so that will cancel out our little fractions here, and that will leave us with 3 minus square root of 3 over 3 plus square root of 3. Now we're in better shape because we no longer have a complex fraction, but we do still have a radical in the denominator, so we still have to rationalize this fraction. And again, we do that by multiplying top and bottom by the conjugate of this bottom. So we're going to multiply top and bottom by 3 minus square root of 3. And again, the FOIL method is how we're going to accomplish this. So in the top, first times first is going to give us 9. Outer times outer is going to give us minus 3 square root of 3. Inner times inner will give us minus 3 square root of 3 as well. And last times last will give us plus 3. Now we have our fraction bar. In the denominator, first times first gives us 9. Outer plus inner will add up to 0 because that's what always happens with conjugates. And last times last will give us minus 3. Now we're ready to combine like terms. So in the top, 9 plus 3 is 12. And for our radical terms, minus 3 square root of 3 minus another 3 square root of 3 gives us minus 6 square root of 3. Then we have our fraction bar, and in the denominator, 9 minus 3 is 6. Okay, now, all 3 of these numbers can be divided by 6, so that means we can simplify. Let's split this into 2 terms. We'll have 12 over 6 minus 6 square root of 3 over 6. 12 over 6 reduces to 2, and for the second term, the 6's divide out, leaving us with minus square root of 3. So the tangent of 13 pi over 12 works out to 2 minus square root of 3. Now, if you think about it, the trigonometry part of this problem was all pretty much done at the beginning. After that, it was a lot of algebra. Think about all that we did. We simplified the signs here, then we eliminated the complex fraction, then we rationalized the denominator, and then we had to simplify the fraction. If we could cut down on some of that algebra, it would make the problem a lot easier. And notice that what caused us to have to deal with this complex fraction was the fact that the tangent of 150 degrees was a fraction. And that's because the tangent of 30 degrees is a fraction. Maybe it would have made our job easier if instead of breaking down 195 degrees into 45 plus something, maybe we could make 195 degrees 60 plus something. So let's try it that way. If we think of 195 degrees as 60 plus 135 degrees, we know that in order to use our formula, we're going to need to know the tangent of both of these numbers. Obviously, the tangent of 60 degrees is square root of 3. Now, 135 degrees is a quadrant 2 angle with a 45 degree reference angle. Tangent values are negative in quadrant 2, and the tangent of 45 degrees is 1. So that means the tangent of 135 degrees is negative 1. Now let's plug into our formula. The tangent of 13 pi over 12, we are now going to think of as the tangent of 60 degrees plus 135 degrees. Using our tangent of a plus b identity, that will give us tangent of 60 degrees plus tangent of 135 degrees all over 1 minus tangent of 60 degrees times tangent of 135 degrees. Now when we plug in our known values, we're going to have square root of 3 plus negative 1 in the top, then our fraction bar. In the denominator, 1 minus tangent of 60 degrees, which is square root of 3, times tangent of 135 degrees, which is negative 1. We'll clean up the signs just like we did before. Square root of 3 plus negative 1, we will rewrite as square root of 3 minus 1. And then 1 minus square root of 3 times negative 1, we will rewrite as 1 plus square root of 3. So you can see that breaking down our 195 degree angle a different way saved us the step of having to simplify the complex fraction. Now we can jump straight to rationalizing this fraction. So to do that, we would multiply top and bottom by the conjugate of the bottom. That would be 1 minus square root of 3. And then using the FOIL method in the top, first times first would give us square root of 3. Outer times outer would give us minus 3. Inner times inner would give us minus 1. And last times last would give us plus square root of 3. In the denominator, first times first would give us 1. Outer plus inner would add up to 0 because these are conjugates. And last times last would give us minus 3. Now let's combine like terms. 1 square root of 3 plus 1 square root of 3 is 2 square root of 3. For our two middle terms, minus 3 minus 1 gives us minus 4. And then in the denominator, 1 minus 3 is negative 2. Of course, this can be simplified, so to do that, we'll break this into two separate terms. 2 square root of 3 divided by negative 2 minus 4 over negative 2. And then reducing here, the 2's will divide out, and that would leave us with negative square root of 3 for our first term. And for the second term, minus 4 divided by negative 2 would give us plus 2. This is the same result that we got when we broke the angle down into 45 degrees plus 150 degrees. It just was a little easier to get to because we did not have to deal with that fractional tangent value. And now let's look at example 2. So again, we're asked to find the exact value of each expression, but this time it looks like they have already plugged some values into one of our identities. So we'll need to figure out which identity they've used and work backwards from there. Here in part A, we have the sine of 40 degrees times the cosine of 160 degrees minus the cosine of 40 degrees times the sine of 160 degrees. So if you compare this structure to the identities that you have on your formula sheet, this minus sign here will tell you that we're dealing with the sine of A minus B identity. And the 40 degree angle is in the place of A, and the 160 degree angle is in the place of B. That means this can be restated as the sine of 40 degrees minus 160 degrees. Now that we see these numbers in the same parentheses, we can do this subtraction. So the sine of 40 degrees minus 160 degrees is equal to the sine of negative 120 degrees. And we can figure out this exact function value using reference angles. Let's draw a diagram. So a negative 120 degree angle would go clockwise 120 degrees. That would put it in quadrant 3, and you can see that there will be here a 60 degree reference angle. Now sine values are negative in quadrant 3, so the sine of negative 120 degrees is going to be negative sine of 60 degrees, which is square root of 3 over 2. And so this original expression from part A is equal to negative square root of 3 over 2. Now let's look at example 2, part B. So here we have tangent of 80 degrees minus tangent of negative 55 degrees all over 1 plus tangent of 80 degrees times tangent of negative 55 degrees. Now if you look at the minus in the top and the plus in the denominator, you'll recognize this as our tangent of A minus B identity. And we see that the 80 degrees is in the A position and negative 55 degrees is in the B position. So we want to write this as the tangent of 80 degrees minus negative 55 degrees. Now, of course, minus negative 55 degrees really means plus 55 degrees. So 80 plus 55 degrees is 135 degrees. Now, it just so happens that we saw the tangent of 135 degrees a few slides back, but we know that 135 degrees is a quadrant 2 angle with a 45 degree reference angle. And the tangent of 45 degrees is 1. So the tangent of 135 degrees is going to be negative 1. And here's part C. Find the exact value of sine of pi over 5 times cosine of 3 pi over 10 plus cosine of pi over 5 times sine of 3 pi over 10. So this looks like the form of one of our sine identities, and it has a plus sign right here, so we know that it's the sine of A plus B identity that they've used. And so we can now write this as the sine of pi over 5 plus 3 pi over 10. Now you could convert both of these into degrees, but I think that the fraction addition is so simple here that we can do the fraction addition just as fast. So pi over 5 plus 3 pi over 10 would require us to get a common denominator. So we would multiply pi over 5 by 2 over 2. That would give us 2 pi over 10 plus 3 pi over 10. That's 5 pi over 10, which reduces to pi over 2. So we're really just looking for the sine of pi over 2, which we know is 1. Now here in example 3, it says write each function as an expression involving functions of theta. So right now we have the sine of 30 degrees plus theta. So right now it's not a function of theta, it's a function of 30 degrees plus theta. We want to use our sine of A plus B identity to rewrite this so that we don't have 30 degrees plus theta inside the parentheses anymore. So here we go, using our sine of A plus B identity, we would have sine of 30 degrees times the cosine of theta plus the cosine of 30 degrees times the sine of theta. And I did not write out the original identity for us this time, but you should have it in your notes or on your formula sheet. Now, plugging in our known values, the sine of 30 degrees we know is 1/2, and the cosine of theta just has to stay cosine of theta. Then we have plus cosine of 30 degrees times sine of theta would be square root of 3 over 2 times sine of theta. This is fine just the way it is because we now have functions of theta only, but you can either leave it in this form or you could combine these two fractions into one fraction with a denominator of 2. And here's part B. So we have tangent of 45 degrees minus theta, and we just want to write this as an expression involving functions of theta only. So of course we want to use our tangent of A minus B identity to do this. So that would be tangent of 45 degrees minus tangent of theta all over 1 plus tangent of 45 degrees times tangent of theta. Okay, now let's plug in the value of tangent of 45 degrees, which we know is 1. So that would give us 1 minus tangent of theta in the top, and that would be all over 1 plus 1 times the tangent of theta in the denominator. Now, there's not much we can do here to simplify, but we do know that whenever 1 is a coefficient, it's not required to be written. So we could also write this as 1 minus tangent of theta all over 1 plus tangent of theta. And now we have accomplished what the instructions asked us to do because we have tangent of theta in the top and in the bottom. We have only functions of theta, and we no longer have a function of 45 degrees minus theta. Now, I do want to caution you about one thing. A lot of students will get to the step after they plugged in their known values, and they will say to themselves, 1 plus 1 is 2, and then they will rewrite this as 1 minus tangent of theta over 2 tangent theta, and they think that they're simplifying. But please notice that this 1 right here is a coefficient of the tangent function, so these are not like terms, and therefore they cannot be combined. So that's a big no-no. We have to be careful not to combine things that are not like terms. And now let's look at part C. So we have the sine of 180 degrees minus theta. Again, we want to write this as an expression involving functions of theta only. So we know that we'll need to use our sine of A minus B identity here. So here we go. The sine of 180 degrees minus theta is going to be the sine of 180 degrees times the cosine of theta minus the cosine of 180 degrees times the sine of theta. And you would get that from your sine of A minus B identity on your formula sheet. Now let's plug in our known values. It might help to look at a diagram. So we know that the terminal side of 180 degrees is going to go through the point -1, 0. So the sine of 180 degrees will be 0, and that's times the cosine of theta. Then we have minus cosine of 180 degrees, so that's going to be minus -1 times the sine of theta. Here we know that 0 times anything would give us 0, so that term will go away. And then we have minus -1 sine theta, so that's just going to be positive sine theta. Now here's example 4, and you'll recognize this as an S and T problem like the one we had in section 5.3. So it says, suppose that S and T are angles in standard position with the sine of S equal to 4 over 5, and S is between pi over 2 and pi radians, and the cosine of T is equal to -5 over 13, and T is between pi and 3 pi over 2 radians. In part A, we're asked to find the sine of S plus T. Now we know that we can do that using our sine of A plus B identity, so let's go ahead and copy that down, but we'll use S and T in place of A and B. So the sine of S plus T will be the sine of S times the cosine of T plus the cosine of S times the sine of T. And all I did here was copy down the sine of A plus B identity, substituting S and T in place of A and B. Now let's plug in the values we know and leave a blank for the values that we don't know. So the first ingredient in our formula is the sine of S. They gave us the sine of S in the problem, so we'll copy that into that place. And the cosine of T was also given in the problem as -5 over 13. And then we have plus cosine of S, which is not given in the problem, so leave a blank for that, and sine of T, which was also not given in the problem. But we do have enough information about S and T to find both of these values. So let's start with angle S. We were told that angle S is between pi over 2 and pi radians. That makes it a quadrant 2 angle. So I'll draw myself a quadrant 2 angle for angle S. And if I close up the triangle, I know that if sine of S is 4 over 5, then the vertical side of my triangle is 4 and the hypotenuse is 5. So now I recognize this as a 3, 4, 5 triangle, but if you didn't recognize it, you would just use the Pythagorean theorem to subtract the squares and find the length of the horizontal side. Now, I need to use this to find the cosine of s. So, since it's a quadrant 2 angle, I know that the cosine value will be negative, and it will be x over r, which is 3 over 5. Then we need to find the sine of t, so let's draw ourselves a diagram for angle t. They told us that t is between pi and 3 pi over 2 radians. So that's between 180 and 270 degrees. That's going to be a quadrant 3 angle. And then we'll close up that triangle. Now, if the cosine is negative 5 over 13, that means the horizontal side here is 5 and the hypotenuse is 13. Now, this one you might not recognize as easily, but if we subtract the squares, 13 squared minus 5 squared is 169 minus 25. That's 144, and the square root of 144 is 12. So our missing vertical side is 12, and now we know that the sine of t is going to have to be negative because it's a third quadrant angle, 12 over 13 because it's y over r. All that's left now is to multiply the fractions and finish with the addition. So when we multiply 4/5 times negative 5/13, without simplifying anything, we'll just get negative 20 over 65. Now, when we multiply the next two fractions together, we know negative times negative will make positive, and there's a plus here. So positive times positive will give us a plus sign there in the middle, and then multiplying these fractions, we'll have 36 over 65. Now, to add, we notice that they have a common denominator, which is great, and all we have to do is add negative 20 plus 36. That gives us 16 for the top and still 65 for the denominator. So the sine of s plus t is 16 over 65. Now in part B, we're asked to find the tangent of s plus t. So let's substitute s and t into our identity for the tangent of a plus b. That's going to give us tangent of s plus tangent of t all over 1 minus the tangent of s times the tangent of t. Now, I've copied our diagrams over here for s and t because we've already done the hard work of finding the unknown sides. We don't need to do it again, but we do need to know the tangent of s and the tangent of t. So for the tangent of s, we know that we're dealing with a quadrant 2 angle, so it's going to be a negative value, and we know that tangent is y over x. So the tangent of s will be negative 4 over 3. And then for the tangent of t, we're dealing with a quadrant 3 angle, so this tangent value will be positive y over x. So tangent of t will be positive 12 over 5. Now we just have to substitute our known values into our formula. Tangent of s plus tangent of t will be negative 4/3 plus 12 over 5. In the denominator, 1 minus tangent of s times tangent of t will be 1 minus negative 4/3 times positive 12/5. Now, of course, we have a complex fraction here. Let's work on simplifying the complex fraction before we do anything else. I see here that the denominators of these two fractions are 3 and 5, and in the denominator, if we multiply these two fractions together, that denominator would be 15. So I need to find a number that 15 and 3 and 5 can all go into. Of course, that number is 15. So what we're going to do is multiply every term in the top by 15 and every term in the bottom by 15. That will look like this. Times 15 for the first term in the top and times 15 for the second term in the top. In the bottom, we have two terms. The first term is 1, so we'll multiply that by 15. The second term is this product right here, so we'll multiply all of that by 15. And now we'll go through and simplify one term at a time. In the first term in the top, this 15 over 3 will reduce to 5, and then 5 times this negative 4 is negative 20. For the second term, this 15 over 5 is 3, so 12 times that 3 is 36. Now for the denominator, the first term is 15 times 1, that's 15. Then let's deal with these signs here. This minus times this negative will give us a plus, and then this 15 will divide out both this 5 and this 3. And if that bothers you, just think about it this way. 3 times 5 is 15. So that 15 cancels that 15, and all we're left with for that second term in the bottom is 4 times 12, which is 48. Now let's do the addition in both top and bottom. In the top, negative 20 plus 36 is 16. In the bottom, 15 plus 48 is 63. So the tangent of s plus t is 16 over 63. Now in part C, they've asked us to find the quadrant of s plus t. Now we actually have no idea about how many radians s plus t would be, but we don't have to. All we have to do is remember that the sine of s plus t came out as a positive number, and the tangent of s plus t also came out as a positive number. There's only one quadrant where sine and tangent can both be positive, and that, of course, is quadrant 1. Now let's look at a couple of proofs together. So here's example 5, and it says verify that the equation is an identity. We have the sine of pi over 6 plus theta plus the cosine of pi over 3 plus theta equals cosine of theta. And we know that our strategy on a proof like this is to always start working with the more complicated side of the equation. So let's copy down the left side of the equation. That's obviously more complicated than the right side. And you can see here on the first term we have the sine of pi over 6 plus theta. So that's a sum. So this is a place where we can use our sine of a plus b identity. So let's start here using our sine of a plus b identity and replacing the a with pi over 6 and replacing the b with theta. That will give us sine of pi over 6 times cosine of theta plus cosine of pi over 6 times sine of theta. Then we'll have a plus sign. And now we can use our cosine of a plus b identity on the next term. So now look at your formula sheet and get your identity for the cosine of a plus b. We'll be substituting pi over 3 in place of the a and theta in place of the b. So that's going to give us cosine of pi over 3 times cosine of theta minus sine of pi over 3 times sine of theta. And just like we always do on proofs, let's draw ourselves a vertical line, and then on the right side, write down what identities we used. We used the sine of a plus b identity for the first part, and we used the cosine of a plus b identity for the second part. The next thing to do is to substitute our known values in each term. So we know that pi over 6 is equal to 30 degrees, and we know that the sine of 30 degrees is 1/2. That's going to be times the cosine of theta. Then in the next term, we have cosine of pi over 6 times sine of theta. So that's going to be cosine of 30 degrees, which is square root of 3 over 2 times the sine of theta. Then in the next term, cosine of pi over 3, which is cosine of 60 degrees, which is 1/2, times cosine of theta. Then we've got a minus sine of pi over 3, which is sine of 60 degrees, and that's going to be square root of 3 over 2 multiplied by the sine of theta. And over here on the right side, I'm just going to state that I substituted our known values. And now let's see what we can do about combining any terms. Notice that here we have square root of 3 over 2 sine of theta, and then the last term is minus square root of 3 over 2 sine of theta. Those are going to add up to 0. And then we can combine these cosine terms. So we have 1/2 cosine theta plus 1/2 cosine theta. 1/2 plus 1/2 is 1. So that leaves us with 1 cosine theta because we combined our like terms, and that is equivalent to the right side of the equation we started with, so that's the end of our proof. And finally, here's example 6, and we're going to verify that this equation is an identity. Sine of x plus y plus sine of x minus y equals 2 times the sine of x times the cosine of y. It looks to me like the only side that we can hope to do anything with is this left side. So let's go ahead and copy down the left side of our equation. And now you can see that the sine of x plus y is going to be a place where we can use our sine of a plus b identity. We'll copy x in place of the a, y in place of the b. So here we go. That's going to make sine of x times cosine of y plus cosine of x times sine of y. Then we've got this plus sign right here. And then the second term from our original expression has sine of x minus y. So that's a place where we can use our sine of a minus b identity. So substituting x and y in place of a and b in our sine of a minus b identity, that's going to give us sine of x times cosine of y minus cosine of x times the sine of y. Let's put our vertical line and write down that we used the sine of a plus b identity and the sine of a minus b identity. Now let's look at what we've got and see if there's anything that can be combined. So the first thing I notice is that we have a positive cosine x sine of y term, and we have a negative cosine x sine y term. Those two will add up to 0, so mark those out and then record over here what happened. And then what's left is sine of x times cosine of y plus another sine of x times cosine of y. So of course when we combine like terms, one of these plus another one of these makes 2 sine x cosine y. And let's write over here that we combined like terms. And now the expression that we ended up with is equal to the other side of our equation, so our identity is proved. Okay, you guys, that is it for section 5.4 as we continue working through chapter 5. We just have one section of identities left, so I'll see you next time. And until then, let me just encourage you to keep practicing and keep working. It takes patience and practice to master identities, but it's well worth it, especially if you will need to take calculus or physics or anything like that later on. Okay, see you next time. Bye-bye.